So hello and welcome to the next video. This will be video on the go, so the quality is unclear now, but we'll try to do it all together. The idea is that I showed you already how AMOS works, and AMOS is the covariance based model. It means it's very robust regarding your theory, and if your theory is not so good, AMOS will find it out. So you will see if there are covariance issues. It means that maybe the theory is not correct and your independent and dependent variable were selected or connected not correctly. In the event of SmartPLS, we have the variance-based structure equation modeling tool. SmartPLS has different advantages over AMOS, but also different disadvantages. One is that it is very theory-driven, so it means your theory has to be robust. If you made a mistake in your theory and you connected something that should not be connected, SmartPLS will assume it is correct and it will make the calculation, although it might be wrong and you will not see this issue. In the event of AMOS, you will see that the model fit is not good, that there are some factors are loading on each other where they should not load on each other, and that the error terms are correlated or not correlated. In the event of SmartPLS, you don't see it. At the same time, SmartPLS allows you to work with smaller sample sizes, not much smaller. It's still recommended to have a big sample size, but SmartPLS is a kind of less sensitive to small sample sizes, just because it will not test all the correlations, all the covariances among the error terms and so on. So it kind of has to run fewer tests for the same data set. SmartPLS also allows you to do something what AMOS does not allow you to do. This is the formative factors. And those who will visit my lecture or visited my lecture should know what is the difference between the formative factor and reflective factor. If we have time, I'm going to talk about it briefly a bit later. So what do we need to work with SmartPLS? First, we need the SmartPLS. SmartPLS 2 used to be free. You just needed to update the license. We have the university license. I have the SmartPLS here. You can install it, and I think you can even buy it for 1 month, and it is not expensive. So if you want to use it, it's a good way to go. SmartPLS works with with a specific type of data sets. It works with a CSV file. Now we have to make again the assumption. Remember, the data set that I use in this video series is the one that I generated, and I generated it to show you exploratory factor analysis. For the confirmatory factor analysis and for the final test, you need a second data set. So assumedly, you developed your scales. In our event, we adapted the scales on behavioral inhibition, behavioral activation, and then we theoretically need to run again the study and make confirmation of the tool that it works and continue working with this tool. In our event, we assume it is the second data set, although it is the same data set. But for your research project, I assume you will have 2 data sets, the one for exploration and the one for actually explanation of what you wanted to find. You go to, the easiest way is to open it in SPSS, go to File, Save As, and you save it as a CSV file, comma delimited, so comma separated value, CSV. And we're going to save it in the folder where I have all my data, CFA YouTube, AMOS. Let's make here a new folder, SmartPLS, and we save this data file as the CSV file. Click on Save. If you do it in different other programs, you can also do it, for instance, in Excel. You have to check what is the CSV, what is the, sometimes it's called comma separated value, but they use the semicolon or they use the tab. In this event, if you import the data, you have to be aware about what the program has used. Also be aware of coding. Usually I think it uses UTF-8 coding, but it can be ACSII coding, and in this event maybe you will need to change coding, especially if you have the Cyrillic letters, so you have German alphabet where you have the A with 2 dots, O with 2 dots, and in this event you have to be sure that the data has been read correctly. Anyway, what is important, SmartPLS work with the numerical data. So if you have some variables which are, let's say, manipulation, you have fear and anger, they need to be coded as 1s and 0s, they need to be dummy coded. SmartPLS will not work with categorical or nominal variables. And if you have like gender coded as 1 and 2, you need to recode it into, let's say, male 100, female 100. So dummy code everything that you have. Otherwise, SmartPLS will automatically assume that female, which is 2, is 2 times male, which is wrong, because it will not work with the data as a categorical data. Let's go to SmartPLS, create a new project. A new project will be called, let's say, YouTube Research Methods class. And we create a new project. Here we need to import data. Just double click it. Go to the data that we need, and the data was stored in the folder CFA YouTube SmartPLS, and here is our data file. Open it, name, okay, let's leave the name as it is, and the data is being opened. Now if you click on the data, you will see how it was coded. The limiter is semicolon, so not the copy. Encoding is UTF-8, as I told you, so check that the coding is correct. Then we have number is US format. It means the comma after 1000 dot for decimals. In Europe would be the opposite. How many indicators? Missing values wouldn't have missing values. I generated this data set, so it has no missing values. The names have been retained, the labels disappeared, and it immediately shows you what are the missing values. We have 0 of them. What is the mean? What is the median? And so on. Now let's go to the, I think we have an issue with this data here, but we don't need them. As you see, it has been important as not as 0 point something, but as 67,000 something. So probably there was a mistake in this data, but the rest should be fine because it is the only data sets or only data entrances that we had with the big numbers and commas. Otherwise, we're good to go. Yeah, the age is here, the median age, minimum age, maximum age, so we're good to go. Let's, it even shows you the kurtosis and skewness, which is also good for reporting. Now we go to our model and we can build a model, and our model, I will just make a dummy model. It is wrong, but I just want to show you how it works. We create a latent variable, which will be, we need 4 of them. We click on select, and if we double click, no, not double click, right click, rename, and this will be our BIS scale. And this will be our, sorry, it was BIS, because we have several BIS or BIS scale. This will be BISRR, BISRR. Then we have the BISD and BISD, and then we have the BISFF. Rename BISFF. So this tool is not meant for the confirmatory factor analysis, but interestingly, there are tests that will help you with the confirmatory factor analysis, help you with the discriminant and convergent validity. This is actually what you need for the confirmatory factor analysis, so it can be a substitute. And many papers that report a model, they also show what are the quality criteria of the data that they have. What you do next, you take this BIS, all items that you need, so, and drag and drop them to, I think it should work. Yeah, it worked. Now we have the BISRR, we drag and drop them to BISRR. Now we have the BISD, and we drag and drop them here, and we have BISF, and we also drag and drop them here. As you see, they're still red. It means we cannot run the model because there are no connections, and we are going to make something very simple. We are going to add our 2 variables, which is anger and here. And why I drop them directly, actually in this event, if you have the circle, it is the latent variable. It means it is unobserved variable that we measured using all these nice tools. So we can move them away that we can see them. And now we have the scales. As you see, still red. It means they are not connected. We'll connect them in a second. What you see here is only one item. It looks like if it is only one item, there is no arrow, just direct connection. It means it is the observed variable. But here it is added with a circle, with the latent variable that we are going to rename anger. But as it has only one indicator, it is not reflective or formative variable, it's just direct measurement. name, and this is our fear. These are dummy coded variable. If fear was seen or experienced, it was 1. If not, was 0. Anger 1 and 0. We had also control group, but we don't have to add it because we compare against the control group. And now let's see if we can make it a bit nicer. Yes, we can make it like this to make it look nicer. And now we can actually connect them. And as you remember, one of the hypothesis tests that we had in the previous videos was to see whether anger and fear are predictors of behavioral inhibition and behavioral activation. So we draw the lines, the tests, and now as everything is connected, they became blue. So we can run the model, but we have not the full model. Now the model is complete. And we can test now whether it all works. And the quality criteria for the items like Cronbus alpha, composite reliability, they will be calculated as a part of this test that we're going to run. So what we do now, we go to calculate, and we have here 2 things that we need to run. The first one, PLS algorithm or consistent PLS algorithm. I don't really know the difference. I think now they ask to run consistent PLS algorithm, but it's fine with the just PLS algorithm. And the second one, bootstrapping. Bootstrapping is the method that helps you understand the probabilities, the p-values. So the first will show you the b or beta coefficients for the standardized values. We have b coefficients here, they are not standardized. And we need to run bootstrapping separately. We start with the PLS algorithm, and here you have 2 things that you can select. I don't know what is Android. We have the factor and path. If we want in this test to see what are the quality criteria, we click on factor. The focus will be a bit different. Iterations, I don't know what to click here. I just leave it as it is. In weighting, I don't need to set anything. We just start calculating, and PLS runs pretty quickly, and now we have the results. If we go to the model, you can see the coefficients here. This is not the probability, these are the coefficients. And you see if it is negative coefficients, means anger reduces behavioral inhibition, but anger increases behavioral activation. Reduces behavioral activation D, and reduces slightly behavioral activation FF. Fear increases behavioral inhibition, which is actually hypothesized, and decreases all other types of behavioral activation, which is also hypothesized. The question is it significant or not? But before we come to significance test, we look at the quality criteria. We need to find the R-squared value model fit criteria. So we go to model fit, and you can find here again chi-square and SRMR. These are the 2 indicators that we also have in Amos. I know how to interpret them. I don't know how to interpret the others, but you can search online what are the quality criteria. Chi-square, we need to find degrees of freedom, and then we can calculate what is the chi-square through degrees of freedom. The question is, where are degrees of freedom? I don't remember, honestly, but we have the chi-square value, and degrees of freedom are usual number of lines that you have in a model. Then we have the SRMR, and SRMR should be, if I remember correctly, lower than 0.9, so we're much lower, so the model seems to look good. Actually, it looks much better than in the Amos, and the reason is very simple, because again, we don't test for covariances, and there are mistakes in the model, most likely, because this behavioral activation, they actually should build a latent, bigger second-order latent factor, and we manage them directly, but SmartPLS will just ignore this fact. Then we can look at the collinearity statistics that will show whether the items are whether they share the common variance, and if the number is higher than 3, then we have a problem. We don't have any problems here. Discriminant validity, we have the nice HTMT test that you can also calculate manually, and if it is lower than 0.8, this is the more conservative value, or less conservative value, more conservative value. Less conservative value is lower than 0.9, then we're good to go. And as you see, we have no issues with the HTMT heterotrait monotrait ratio. This is another description, so it seems that we're good to go with our model. And the cross loadings, the table, you can just copy paste it in your work. And what we do, we usually do not display the items that are higher than 0.3, because below 0.3 is everything. Actually, below 0.4 is everything is irrelevant. So it will be clean factors, as I have shown you in the exploratory factor analysis. It just shows the full table. In our video with the exploratory factor analysis, I just asked not to show small values, because this value wouldn't have been shown up to here, but BSD, you see these big values would appear here. In your table, when you report the results, you just delete anger and you delete fear, just because what you are interested are these latent factors, that they are measured correctly, that they are not co-measuring each other, that everything is fine. Let's see BSD. You see high loading on one factor, BSD, all good, and no other high loadings here. So it will be just empty, and these items will be shown here. So you can copy paste it and hide all the items which are lower than 0.4. You can do it in Excel, or you can just manually delete them in Words. It doesn't matter how you repeat it. Construct validity and reliability, and here we have actually two important things. We have the Cronbus alpha and we have the composite reliability. For this model, Cronbus alpha is sufficient because they all have the same scales. They're all Likert scales, I think 4 Likert scales, which is untypical for me, but it is from the paper. They used to measure it with the 4 Likert scales. I would go always for 7 Likert scales. 9 is too much, or 100 with a slider, otherwise 7. Composite reliability is the factor that is less sensitive towards different measurements. So if you had items, some of them 5 Likert scales, some 7, some 4, then composite reliability will bring you better results or more correct results. So as you see, all the things you have to calculate manually, or like HTMT, you have to calculate it manually, because SPSS cannot do it. And I give it as a task to my student to calculate additional statistics to find a way to do it. It's not hard to do, it's just a simple Excel calculation where you can see in how much factors are correlated or not correlated. And it means we're good to go. The model seems to be good, R squared, and we can see how much variance we explain in dependent variable through our independent variables, or by our independent variables, and see it is not much. In the event of BIS, it is 13%, which is good. Actually, everything that is higher than 15% is already good. We have very low R squared here, but think of the following: any effect that you will find is already good. You found some effect. For a good journal, you need to have more explanative power. Okay, now we go back to our model, and this time we are going to repeat this calculation with the path, focusing on the paths. So the values will not change much, but each time you run the model, it runs on a certain number of bootstrapping runs on a certain number of cases. So bootstrapping works in the following way: it takes your data set and randomly picks some of the items and relates them, and then repeats it with the next random selection. It means you can run bootstrap. If you have only 100 cases, you can run with a bootstrap a kind of thousands of cases, and it will show probabilistically whether the relationship is present or not, and what is the likelihood or probability that they occur. So we go to our model. We can even compare them, but I don't think it is our goal to compare. Let's see. Yeah, you see small differences, 0, 133, 0, 134, just because the focus is set on the path. You can close this window after you copied all the data that you needed. And we have also outer loadings, inner loadings, where you can see what is loading where, what are the loadings. And you see here, for instance, this loading I told you should be about 0.7. 0.6 is less conservative value, so we can retain it as less conservative value, but actually we have the loadings here. So if you build a nice model where you want to show the loadings, you run this factor analysis and you copy paste these loadings here. I'm going to show you briefly in the paper that I showed in the previous video. We made a nice model that we depicted, and this was the structure model where we have shown all these characteristics. And just going to find the model. Here we go. And if we zoom in, these are the factor loadings, and you can find these factor loadings in this table. Okay, so let's go to PLS algorithm. It has shown we have some effects, but we need to know whether the effects are significant. That's why we go to the model, calculate, and run bootstrapping. Bootstrapping, how many subsamples? I think it is recommended to have 5,000 subsamples. I am going to stay by 500 for a simple reason. 5,000 will take too much time, and we don't want to have too much time spent in this video. Then we go to PLS path, all is correct, and we start calculation. By the way, if you go to this consistent bootstrapping, it will automatically set all these hacks, all these check marks as they should be, but you have also less control over what you actually find. And here we go. This is the p-values, what we can find here. Anger has no significant impact on BSD, no significant impact here, but anger has significant, statistically significant impact on the BIS scale, and it is b value of minus 0.6162. Weakly significant on BSD has here strong significant BS on FF and no other significant effects. And if we now go back to the model, what we see now here are the T values. T values show you both the effect and also the significance. If the T value is higher than 1.95, it is statistically significant. I think it's 1.95. So you see, this is definitely significant and strong effect, positive effect. Here we have no significant effects, and again we have here a strong significant effect, and one is close to the level of significance. This is the weakly significant, probably the one that was weakly significant. Okay, with this in mind, I think you know now how to test this model, and in the next video I'm going to show you what else you can do with SmartPLS. See you in the next video.